In this video, I want to talk about how to estimate the parameters of a multinomial logit model for the outcome of a particular team match. And the way that we're going to estimate it is we're going to use an n estimator based on, well, you could say it's just a maximum likelihood estimator, where the choice probabilities are computed based on this formula with utility indices. And each of the utility indices are just linear indices, an x beta if you will. And we're normalizing the coefficients for the first alternative to zeros. So we're just estimating j minus 1 coefficients on k variables. Alright, and we're going to do max rescaling along the way where we subtract the maximum for each of the utilities. And here's the function in the utility function in all its glory. It starts by checking input dimensions and making some assertions to throw errors if we're putting wrong things in. Then we compute our x beta, which is x times theta. And then we sum over the middle axis. And here we can see that our x shape is n by k by j minus 1, or at least that's how we're thinking about it. So the middle dimension k is where we have the regressors, and the third dimension is denoting the different outcomes, so a draw and a win respectively. And then we construct our normalized alternative utilities, which are zeros, and we put them in front of our x betas so that we have a full n by j matrix of utilities. And then finally, we subtract element-wise an n by 1 vector. So an n by 1 subtracted from an n by j, Python will assume that we want the n vector subtracted in each of the j columns, which is how we want it. And what is that n by 1 vector? Well, we take utility and we find the maximum over axis 1, so in each row, the maximum utility for each individual. And then we return the utilities. And we have a choice probability function which just computes utilities and then computes a denominator which sums the exponentiated utilities along the first axis, so along the sums it over alternatives j, and ensures that we have an n by j or n by 1 vector coming out of it, not a flattened n array. And then choice probability matrix, which is n by j, we find that by dividing the exponentiated matrix of utilities by this vector that is the denominator. So that's how we compute choice probabilities in this model. We also have a log likelihood function here, which does the same thing, computes utilities and computes the denominator. And then we find the utilities for the chosen action. And the way we do that is we take a long axis, so we take our utility matrix, which is n by j, and we evaluate it at the locations indicated by the vector y. And remember that y is a vector that takes values 0, 1, or 2. So we can use y to look up in an n by j matrix. So if we have I'll show that in a second how that works. So this is basically taking the matrix n and picking the column indicated by y, and y is our outcome, the outcome of the match, lose, draw, win, corresponding to 0, 1, or 2. And the 0th column of u is the lose column, which is our normalized alternative with the 0 utilities. So that's all good. And now yi is going to be just a vector. So we can take the exponential value and make an element-wise division by the denominator. So for each individual I, we divide the exponential value of the utility by the denominator. And then they have the choice probability for so that's the likelihood, and then we take the log of the likelihood, log of the probability. And actually an alternative even smarter way of doing this is if we take the log of a fraction, then we get the log of the what's on top, and that eats the exponential function, minus the log of the what was in the denominator. So this is an even better way of writing the log likelihood, because we're avoiding an exponential function, and we're avoiding a division operation. Subtraction is a much more stable numerical operation on a computer. Great. So this is our log likelihood function. So our Q function, the criterion function, which returns a scalar, so uppercase Q, is then just going to be the negative of the average log likelihood. And this function, as you can see, will be reading y and x in from global memory. So we can only evaluate it at whatever y and x are in global memory space. And this is because we'll be giving it to a minimizer. So we can already now say, if we define a theta naught, here we go, then we can evaluate our Q function at that value. And we could imagine that what happens if we divide it further by 10, are we getting a lower value of the criterion function? And we are, and here it didn't really get much better, and now it got worse, and so on. So we could start, here I'm just manually searching over the parameters by changing all of them at the same pace, right? And then the optimizer will be changing each of them once we get to that point. But before we get to optimization, I just want to show you a little bit of what's coming in and out of these different functions. So again, let's construct x here, and let's clear all outputs. Let's construct x. So here we have it. This is our 3 vector, and let's compute utilities evaluated for each of these 3 individuals. These are the characteristics for the first individual, for outcome j equals 1 and j equals 2, and for this is the betting probabilities, this is the home dummy, and this is the constant term of the model. So let's compute the utilities. Are the utilities, having time traveled back and forth for confusing myself a bit. And of course now we have 3 rows, because we also have a row for our normalized alternative. And the reason for the negative numbers will become clear. It's because we've max rescaled the utilities. Let's see how it's computing these numbers. So first, recall that theta naught needs to be multiplied by each of these blocks, and that's what NumPy correctly understands when we write x times theta naught. And so now x times theta naught has the same shape as does x. And it's the middle dimension that we want to sum over. We want to sum over k. So we're going to write sum axis equals 1. We could have chosen 0, 1, or 2. We can compute all those sums, but 1 is the one that makes sense, where we're summing over the characteristics. And this is the what's coming out. This is the sum of this first row here is the sum of 0.02 plus 1 plus 0.1, so that's 0.227, and that's what it says here. This is the sum of these 3 numbers. Alright, so this operation here will give us our xb term. And then what we do is we stack horizontally, and we add a column of zeros next to it. And the column of zeros in this particular case is 3 by 1. So this is our utilities, and then what we do with that utility matrix is that we find the maximum along the axis 1, so horizontally. And then we want to subtract the maximum for from all of our elements. And let's see if this actually gives the same thing, or if we do have to reshape here. Yeah, that does make a difference. So as you can see, this is an example where actually NumPy is allowing me to subtract the maximum. Let's write that. Let's print them out here. Here's u, and here's the maximum along the first axis. As we can see, the maximum in this row is 0.25, the maximum here is 0.246, and the maximum down here is 0.238. So if we just write u minus this, we're getting all kinds of weird things going on. I'm actually not sure exactly what it's doing here. Probably it's confused because it's a 3 by 3 matrix. But when I reshape it and so that it's a vector that's standing up, things work well. So the 0 here becomes the minus 0.25. So this is the max rescaled u, and we can overwrite u by this, which is equivalent to writing u minus equals. So now our u has been max rescaled. And we can see that this is what's coming out of our utility function. All right, then we can compute choice probabilities based on these. It's just the exponentiated values divided by the sum of the exponentiated values. And as you can see, 0 is the largest value here, and that's the largest choice probability down here. And this one's pretty close to 0, so that's going to be pretty close. So as you can see in this row, the most likely outcome is a win, but the draw is almost equally likely for this particular observation. All right, so those are the choice probabilities computed based on the utilities. Next up, we can ask what did actually happen for the first 3 rows. Well, the outcomes were 1, 1, and 0. So draw, draw, loss. All right. Then what we want for our likelihood function is the log of the choice probability for those outcomes. So for this outcome, for this one, and for this one. So we want the 0.354, 0.355, and 0.283. So there are 2 ways of doing that. For instance, we can find the first one by saying the 0th row and the first column. And that gives us this number. And we can do the same with the second row, and we want the same column actually. That's here, and the final one that we want is 2, 0. But how do we get them all next to each other? Well, here's the syntax you have to use. First you tell it what are the rows you want, row 0, 1, and 2, and what are the columns that you want, 1, 1, and 0. And that will print it out in a nice vector form. And alternatively, we can use NumPy's function take along axis, where we give it the choice probabilities and then a vector of indices. Maybe it would be more instructive to say, okay, what we're doing here is we're giving it y up to the for the first 3 values in y, and it will actually complain about this because y is not a flattened, is a flattened array rather. So it wants to see a 3 by 1. No, oh, that didn't work. Let's revert back to the original. Here we go. Yeah, so it has to have the right dimensions for this to work. And this one can alternatively be written as range of 3. So in general, range of n and y, but now we only have 3 in our probability matrix. So in order to do that, we could evaluate our choice probabilities for all of our observations. And here we have the probabilities for the selected, or for the actual observed outcomes. And so the log likelihood would just be the log of these. And so let's double check that our log likelihood function does actually give us this. If we give it y, x, and theta naught, here we go. And that's indeed the correct numbers that we're seeing. So that was lucky. All right, now we're ready to run the optimizer. And for the optimizer, we just have to tell it what function it's optimizing and give it a vector of starting values. So let's see what happens here. I'm printing whether it was a convergence success and number of iterations here. So it was a success after 42 iterations, and here are the estimated beta coefficients. So we have a coefficient on the B365 probability of a draw, how it affects the outcome draw, and it also has the Bet365 probability of win affecting the outcome win. And we have a constant term in the draw and a constant term in win, and the home dummy affects draw differently from win. And how do we interpret these coefficients? Well, they're interpreted relative to the normalized baseline, so loss. That is, the probability of winning, or the utility index for winning, is 0.2 higher relative to the probability, to the utility index of losing. In other words, being on home turf increases the index for winning relative to that for losing, and it increases the utility, if you will, of a draw by more than it increases that of winning, because this coefficient is larger. And we can see that the constant terms for the two are about equal. And here's our theta matrix, which we can print out. And here they are. So these are the betting probabilities, the home dummy, and the constant term. And again, we can use pandas data frame to format this nicely and tell it that we want the columns to be draw and win, respectively. Great. Okay. Then here's some code that you can look at your own leisure, which evaluates the predicted probabilities when we compute the choice probabilities for those estimated parameters coming out of the result struct out of minimize. We evaluate what the probabilities are. We evaluate those probabilities in the observed outcomes. So we take the probabilities of the outcome that actually occurred, and then we can look down. That's prob I. I don't think we actually use that for anything. Anyway, we show all three probabilities here, and so in this particular match, which was with, let's look at FC Porto here, Bet365 gave a 73% probability of a win, and our model is giving a 78% probability of a win, and that was in fact what happened. So in this particular row, our model is doing better than Bet365. But we're also allowing us to use Bet365's odd or imputed probabilities in addition to more variables, so it's not really surprising that we're doing better. And here I think we're plotting the two next to each other so that we can just look at what is the this is the prob I that we created up here, and together with the PRI, together with the probabilities from loss, draw, win from Bet365, and also doing a take along axis for that matrix. So here we can directly compare the probability for the actual outcome for us and for Bet365. So we can actually see that if we take the average here, we are actually doing worse in terms of the average probability of the outcome. So we're only predicting on average a 41% chance of the actual outcome, whereas Bet365 is giving us a 41.6%. That's pretty remarkable. And we can see how often, or what the average difference is, and it's negative, so we're doing worse. And how frequently are we doing better? Only 49% of matches. That's pretty interesting. But the explanation turns out to be that we're doing worse in terms of average probability because we're doing better in terms of the average log probability. Because in fact, we've chosen our parameters to maximize the average log probability. So we could envision an alternative M estimator where we were just maximizing the average probability, but then we're no longer in the maximum likelihood world. But if that's our objective, to do better, then we can choose that as our sample criterion that we're trying to maximize. But regardless, this has shown how to compute a model which uses a very, very small number of variables. It only uses the 3 predictions from Bet365 and a home dummy, and is giving out some probabilities for matches. What we can then go back up and do is we can expand the list of variables. So for instance, we can set small scale equal to false here. And now we'll instead be using a much longer list of variables that gets specified here, and hopefully in a small second will be printed out below. So now we're not just using these 3 variables and the home and constant terms, but we're also using the predictions from all of the other betting firms, which is also what we did with that linear model in a separate video. So let's see what happens when we get down here. Took a while to estimate. This time we're estimating a lot more parameters. As we can see here, there's one for all of the betting firms, and they have a separate, their draw probability. We can be loading differently on draw and win probabilities if the firms are differently able to estimate the draw and win probabilities respectively. And so now what turns out at the very bottom is that we're not doing much better in terms of average probabilities. So the final word isn't said with this particular model, but perhaps there's some other expansion we can do, adding even further, even more variables to try and see if we can do even better